Hi everyone! In this video we're going to use everything that we've learned so far about linear association and linear models to analyze the given bivariate data. In this data set we have information about ages and prices of some Honda Accords. So these are ages and these are prices. And our work will be guided by questions listed in this exercise. First, we need to construct a scatter diagram by hand, and for that we need to determine which variable is explanatory and which one is response variable. Let's see, we have age and price, so let's think which one might affect the other. So is it age that affects the price or price that affects the age of a car? Well, using common sense, we can agree that age of the car might determine or might predict the price of the car. So explanatory variable is age and the response variable is price. When we construct a scatter diagram or scatter plot, the explanatory variable is always the horizontal axis and the response variable is the vertical axis. So here I'm going to label the horizontal axis age, and it's in years. And the vertical axis I labeled as price for the response variable in thousands of dollars. Now I need to number age. So for age, let's see, the smallest age we can see in the data set is 3, the highest is 12. Remember, when we label a number line, we have to spread out numbers evenly and increase by the same amount. So since we don't have very high numbers here, I'll just number it from 1 up to whatever I can fit in here. So it's 1 through 15. Next, to label the vertical axis, I make a note that the lowest value in the data set for the response variable is 7 and the highest is 17. Okay. I think I'll start at 7. Remember, we don't have to start at 0. We can start at any number when we construct a scatter diagram. And then I'll just increase. I think if I increase by 2, that will do it. So 9, 11, 13, 15. Okay, yes, here's 17, and then 19. Okay, perfect. And now I'm looking at pairs of numbers, the ordered pairs. The x-coordinate of point that I'm going to plot is going to be 8 for the first point, and then the y-coordinate is 13. So I'm looking at the values of the explanatory and response variables as ordered pairs. So 8, 13 is the first point, 7, 9.2 will be the second one. So 8, 13, 8, 13. Here it is, 7 and 9.2, 7 and then just a little bit above 9, 12, 7 is the third point, 9 and then 9.9, almost 10, is about over here. So I'm going to continue that pattern and plot the rest of the points. Okay, so that's our scatter diagram that we constructed based on the given data set. Next, the question is, does a linear association exist? So as we look at the scatter diagram, I think we can recognize a pattern that has decreasing direction. But for a question like that in statistics, I shouldn't just rely on how it looks to me. We have certain steps that we can do to confirm if the linear association exists. So to answer this question, we're going to use the correlation coefficient. So step 1, find the correlation coefficient. To find the correlation coefficient, we're going to use the TI calculator. We start by entering the given data set. So I press on Stat and then Enter. Here I will clear the old information I have in the first 2 columns. Okay, now I'm going to enter the given data set. At this point, I always make sure that I have same number of entries in both columns. This way I can catch mistakes where I forget to enter one of the numbers. Okay, and next we press on Stat again. This time we're going to go to Calc tab, and then go down to line number 4, Lin Reg. I confirm that my data is in list 1 and list 2. Go to Calculate and press Enter. Okay, so here I can see the correlation coefficient. It's denoted by lowercase r. It's negative point, and then I have all those numbers. I'm going to keep 3 decimal places, so 874. By the way, if your calculator doesn't show you r, the correlation coefficient, it means that you need to turn on the diagnostics. We talked about that in the video where we learned how to find the correlation coefficient. Okay, so I'm gonna write this down. R equals negative 0.874. And now in step 2, we're going to use the critical values for correlation coefficient table to determine whether this correlation coefficient indicates the existence of linear association or not. Okay, so step 2, use the critical values table. And for that table, we need to first look up the corresponding sample size. So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 7 values entered for each variable in our data set. So we're going to look up sample size 8. Here it is. And it corresponds to the critical value 0.707. So what we do, we take the absolute value of the correlation coefficient that we determined. So the absolute value of negative 0.874. Well, the absolute value of a negative number equals to a positive number. So it's positive 874. So basically we just drop negative sign. And now we compare that to the critical value that we looked up in the table. Once again, it's 0.707. I'll put here 0.707. And I need to determine whether the correlation coefficient greater or less than the critical value. Well, we can see that the correlation coefficient is greater than the critical value. So that is the critical value. And that means that the linear association exists. So the correlation here is strong enough for us to say that, yes, linear association exists. I made a note of that. And if we determine that the correlation coefficient is less, or I should say absolute value of the correlation coefficient is less than the critical value, well then the conclusion would be that linear association does not exist. Okay, well, let's move on. The next question is asking us to find the least squares regression line. So first of all, I have to note here that since linear association exists, it means that we can create a linear model that would describe this relation between the two variables. And I also forgot to mention that at the beginning we said that, well, it looks like there is some kind of pattern, and well, we just confirmed that there is linear association. And we also talked about how the direction is negative. And once again, notice that correlation coefficient has a negative sign, so that confirms that association is negative. So in other words, the sign of the correlation coefficient tells us the direction, positive or negative, and the absolute value of the correlation coefficient describes the strength of association. Okay, find the least squares regression line. Well, we're going to find the equation of that line that can be used to model the association. For that, we're going to use a calculator again. So to find the equation of the least squares regression line, we start by entering the data set, but remember we already did that here when we had to find the correlation coefficient. So that part is done. So we can right away go to Stat. And again, we go to Calc, and actually we go to the same place where we just looked up the correlation coefficient. Now we're going to look at that window again, so everything stays the same. But this time we're going to focus on the first 3 lines. So remember, that's where we found the correlation coefficient. But yeah, now let's look at the first 3 lines. So here is the form of the equation, of the least squares regression line equation. I'm going to copy down what I see on the screen. So on the calculator, I see the following. It says y equals ax plus b, and then I'm given both a and b. I'm going to copy these values and I'll round them to 2 decimal places. Well, actually the first one, a, if I round to the decimal places, it's going to be negative 0.90, so I'll just say negative 0.9, like that. And then b is 18.42, right? Since 8 follows 1, I have to round up, so 18.42. And now to obtain the equation, what I'll do, I'll just have to plug in the value of a over here, so that becomes number that's in front of x. That's the slope. We're going to talk about that later. And then a value of b, I'm going to plug in over here. So then my equation will look like this. It's going to be y hat, and remember that when we write equation of the least squares regression line, we don't use y because just y represents the actual or observed values from the table. So the response variable from the table, but y hat indicates predicted values. Predicted value of the response variable, and then it's negative 0.9x plus 18.42. Okay, so we found the equation of the least squares regression line. Let's move on. In the next step, we're being asked to draw the least squares regression line on the scatter diagram of the data, so on the same xy plane. How do we graph this equation? Well, using same methods that we use in algebra. And there are several ways how we can graph a linear equation. That's how it's called in algebra, in our case, regression equation. But the one that I think works the best is the method where we have to find and plot 2 points, because generally 2 points is enough to graph a straight line. So we're gonna use, it's called point plotting method. So for that, let's organize our work in a little table. We're gonna have 2 columns in the table. The first column is for the explanatory values of the explanatory variable, and the second column for values of the response variable, which is y hat, the predicted values of the response variable. And what we'll need to do, we'll need to pick 2 values, any 2 values of the explanatory variable. As I said, well, it can be any 2 values. We'll try to stay within the scope of the data set, so we don't want to go outside of the smallest number or the highest number, but it can be any. Well, what I find the best is to use actually values from the table, and specifically I pick the smallest and the highest because I don't want those 2 points to be too close to each other, because then there's a good chance for shifting a line a little bit when you graph it. But when 2 points are far away, then you graph line more precisely. Okay, so the smallest value is 3, the highest is 12. That's what I'll use. But again, you can use any values that are not even listed here. So 3 and 12. I added the note here that in general you can pick any values. We chose mean and max from the sample data. Okay, so now what do we do with the chosen values? We have to plug them into the equation. So basically we're saying, well, when x equals 3, what will be the corresponding value of y hat? Well, we just plug in 3 for x here and then compute y hat. So y hat equals negative 0.9 times 3 plus 18.42. I'm going to enter that in the calculator. Don't forget that when you enter negative numbers, you have to use this button over here for a negative sign. So negative 0.9 times 3 plus 18.42, 15.72. Value of the response variable y hat. That corresponds to the value of the explanatory variable x equals 3. And that, or those two together, they make a point. And that point has coordinates 3 and then 15.72, which will, round up, will approximate it when we're going to plot it. And yeah, and that point we'll plot in a minute. So now let's find the second point. And we're going to repeat the steps. Oh, I should have said 12 here, right? Not 2. I'm sorry if I confused you. So that's 12. We're going to plug in 12 into that same equation, the regression equation. Negative 0.9 times 12 plus 18.42. Times 12 plus 18.42, that's 7.62. So the second point will be 12, 7.62. Okay, so let's try to plot them. Okay, first one is 3, 15.7. 3, 15.7. Okay, so 3, and then I have to go up to 15.7, so close to 16 right here. And the second point is 12, 7.62, so 12 and then 7.62, so it's close to 8, somewhere over here. Okay, so this point and this point, these are the ones that will belong to the regression, least squares regression line. Now I'm gonna find the straight edge and connect those two in a straight line. Okay, so here's the line. Okay, let's move to the next question. In this question, we have to use the equation, that is regression equation that we found, to predict the price of an 8-year-old Honda Accord. We also need to find the difference between the observed price and the predicted price for an 8-year-old Honda Accord. Okay, so let's do the first part. So here it says to predict the price. Remember, the price is the response variable. Well, it says predict the price, so we need to find the predicted value of the response variable. So that is y hat that we need to find given the age of the car. So that is age. That means that we're given the explanatory variable x. So to find the predicted value, knowing the value of the explanatory variable, we just have to plug this value into the equation, similar as to how we just did it when we had to graph the line. So y hat equals negative 0.9. This time it's going to be times 8 plus 18.42. That's 11.22. So that is the predicted price of an 8-year-old Honda Accord. I'm gonna write the answer in a full sentence. Okay, I started the sentence and I want to finish it together. So I wrote the predicted price of an 8-year-old Honda Accord is 11.22. But I also need to write down the units. And here I have to be careful and remember the units for the explanatory variable. I can refer again to the table. And remember that price is given in thousands of dollars. So that is $11.22 thousand, not just $11, right? That would not make sense. So $1,000. Usually we don't say it like that. So I'm gonna write down here in parentheses the kind of the standard form of that number. So that's $11,220. That's what it is. Okay, so we answered the first part. Let's answer the second part. It says find the difference between the observed price and predicted price. So the observed price is the one that we have in our data set in the table. So observed price minus the predicted price, y hat, will be, let's look at the observed price. For 8-year-old Honda Accord, we have the price in the data set $13,000. So 13 minus 11.22, that's 1.78, well, for $1,000, or I read like this, $1,780. That's what it means. But I'd like to point out that what we just found, that's what's called residual. Remember when we talked about residuals, we said that's another word for an error. So that's an error we are making when we're using the regression equation or the least squares regression line to predict the price of a 8-year-old Honda Accord. So that is residual. Residual. And what can we say about our prediction? Is it underestimation or overestimation? Well, if the observed price is $13 and the predicted is $11,220, well, it is underestimation. So when the residual is a positive number, it means that we're looking at underestimation. When the residual is a negative number, it's going to be overestimation. So that is underestimation. Okay, let's move on. In next question, it says use the equation, again the regression equation, to predict the price of a 9-year-old Honda Accord. By how much do predictions in part E and F differ? Does this number look familiar? Okay, let's do the first part. We're going to do it quickly because, well, that's pretty much the same thing we've already been doing over and over again. It's just now we have to plug in 9 for X. Let's see what's the point of that question, because there is a point to this question. We're plugging in this number over here. Okay, let's see. Negative 0.9 times 9 plus 18.42. That's 10.32. Okay, so that's the predicted price, 10,320. Okay, and then we need to find by how much this predictions in part E and F differ. Well, let's take prediction we just found in part E, 10.32. So that is 9-year-old car. And let's subtract the predicted price for 8-year-old car. That's 11.22. Let's see what that difference is. 10.32 minus 11.22. Okay, that is the difference. Negative 0.9. And does this number look familiar? Have you seen it before? Well, it's actually here right in front of us. That's the number that stands in front of X in the regression equation, right? Is it coincidence or not? Well, no, it's not. So that number is the slope, or in statistics we call it rate of change. We're going to talk about it in the next question, but I'll just write down here slope, which is same as rate of change in statistics. And what does this number mean in the context of this operation that we just did? So we subtracted prediction for 9-year-old car and 8-year-old car. So looks like the price for 9-year-old car, for a car that's 1 year older, is less by this amount. By the way, what is this amount? That is $900, right? So in 1 year, we predict that in 1 year price will drop. And by the way, that's what the negative sign indicates. So price dropped by $900. Price dropped by $900. So we're gonna talk more about this in the next question. So let's try it. Okay, so it says interpret the slope. Let me write down the regression equation one more time. X plus 18.42. So as we already said, this number that stands in front of x in a linear equation, or in our case, we call it regression equation, it indicates the slope. That's mathematical name for that number. In statistics, we call it rate of change. And basically, this number tells us at what rate the response variable, whatever it is increasing or decreasing as the explanatory variable increases. So to make sense out of all that, let's do the following steps, and I recommend you doing these steps every time you need to interpret the rate of change or the slope. So rate of change, I'm just going to write it down one more time, is negative 0.9. Okay, what do? You rewrite it as a fraction with 1 in the denominator, so it's negative 0.9 over 1. Any number we can put over 1. But we really want to look at the rate of change as the quotient, something with a numerator and denominator. And the top value will always represent response variable. And in our case, it's price, so I recommend even writing out what it is. And the bottom number is explanatory variable. And that is age. And once you look at the description of each variable, then it helps you to put this all together as interpretation. So we're going to say that the price of Honda Accord decreases or drops, and that's one more thing that I need to note. So rate of change is going to be either positive or negative. So that means that this numerator will be either positive or negative. So if it's negative, then the word will be, the key word for that will be decreases. So it means that the response variable decreases or drops. And if the sign is positive, then it's going to be increasing. So the price of Honda Accord decreases by this amount. Well, this is $9,000, so it's $900 per 1 year. This is age, right? In years. So per 1 year, or we usually say per year, or we can say every year. So here we change wording a little bit, but you got the idea, right? So you have to mention both variables in this interpretation, and at the end, we're going to say on average, because that's the average. Of course, it can be more or less, but on average, that's going to be a rate at which price of Honda Accord will decrease every year. I'm going to write this all down. Okay, so price of Honda Accord decreases by $900 every year on average. So the key parts of this interpretation should be first mentioning the response variable, then saying whether it decreases or increases by what amount, and that's going to be your numerator. Decreases or increases will be the sign, positive or negative. And then here it's going to be 1, but units will be different. Every year, every mile, so on and so forth. And then you're also going to always say on average, because it's the average rate of change. So that's how we interpret the slope, or the value that stands in front of x in the regression equation. And finally, the last question, in which we need to interpret the y-intercept. So the y-intercept graphically is the place where our line crosses the y-axis, but in the regression equation or any linear equation, that's the number at the end of that equation that's being added or subtracted. So before we even attempt to interpret the y-intercept for our station, we have to answer two questions. And the first one is, 0 a reasonable value for the explanatory variable? Remember, explanatory variable is x. In our example, x is age of a car. So in other words, can age be 0? Yes, car is 0 years old when it's a brand new car, right? So it is reasonable. It's not reasonable, for example, if explanatory variable is height. Can height of a person be 0 inches? Well, no. So that's when we're going to say no to this kind of question. But in our case, the answer is yes. I'm going to write down the complete answer. Yes, a car can be 0 years old. It's a new car. The second question. Do any observations near x equals 0 exist in the data set? Well, let's look at our data set. It's right here. Do we have any values close to 0? Well, we do. So we have x equals 3, which is pretty close to 0, right? So we're gonna answer yes. And since we answered yes to both questions, then we can interpret the y-intercept. And if answer to either of these questions is no, then we do not interpret the y-intercept. We just say it's not appropriate to interpret the y-intercept. But in our case, we continue. So I'm going to write down the regression equation one more time so that I can emphasize where the y-intercept in the equation is. So that's this number right here. Y-intercept. And since it's a y-intercept, by the way, let's look at the graph and confirm it graphically. So here's our line. Where does this line cross the y-axis, the vertical axis? Well, right here. And if we look at it, then yeah, it's going to be about 18.42, right? Well, it's actually a pretty good graph that we have here because it does look very close to 18.4. So in order to interpret the y-intercept, like its meaning in the context of our example, it's always helpful to think about the actual coordinate of that point. What is the coordinate of the y-intercept? Well, a y-intercept will always have the first coordinate 0, and the second, the y-coordinate is, well, 18.42. And now as you look at this order pair, you have to remind yourself that the first value is age, and the second value of the response variable is price. And as you look at them this way, it helps you to put things together in a sentence. So in other words, this is the price, $18,420 is for the car that's 0 years old. So it's the estimated price for a brand new car, for a brand new Honda Accord. So that's the meaning of the y-intercept. So once again, it's always going to be value of your response variable when explanatory variable equals 0. Let's write the interpretation down. Okay, so the estimated price for a brand new Honda Accord is $18,420. And I'll make a note here, brand new. Why we're saying brand new is because in the context of our example, that's what means that x equals 0, which is age, I should say age equals 0. Age equals 0. So that's how we interpret the y-intercept. And there's one last note here that says that in general we should not use the regression model to make predictions. So that's kind of to everything that we've done so far. We don't use this regression equation to make predictions outside the scope of the model. So in other words, today or right now, to answer many of these questions, we have to plug in different values of x into this equation. So we don't do that if values of x are much larger or much smaller than those that are observed, because that's when this model becomes less and less reliable. So it's the most reliable. Let me go back to the model itself, to its graph. So this model is the most reliable when we stay within the scope of the given values. And when we go outside of the given values, it's less reliable. So that's important thing to note. So these are many things that we can do with a linear regression model, and we also learned or refreshed how to find the model itself.